So we're going into our final lesson, and this is going to cover geometric sequences, which is just another name to look at exponential functions. If you recall back from a while ago when we covered arithmetic sequences, that dealt with linear functions. So we were looking at a line of numbers or a table of numbers, and we had to determine if it was arithmetic or not. So that just meant, is it linear or not linear? And if it was linear, then it was an arithmetic sequence, meaning that it went up by the same value, like 1, 3, 5, 7 is the addition of 2. So that was actually the change or the slope we viewed as 2. Or it could have been subtracting, so something like -10, -13, -16. We looked at a change of -3. Geometric sequences is at the end of the exponential unit because it is a multiplier or a divider. So when we look at the values, just like we did when we were graphing exponents, the values are going to either multiply to get to the next sequence or you can divide. So something like 2, 4, 8, 16. We're looking at a sequence of a pattern of multiplying by 2. Or it could be the opposite. We could go from 20 to 10 to 5. This is dividing by 2, which is the same as multiplying by a half. So the first set of examples, we just want to determine, is it arithmetic, is it geometric, or is it neither? So is it linear? Is it exponential? Or is it neither? Okay, so the first sequence, we have to figure out what this pattern is. So I'm going from 120 down to 60, down to 30, down to 15. It looks like we are following a pattern of dividing by 2, which is the same as multiplying by 1/2. So this is a geometric sequence. Example B, if I look for a common multiplier, we multiply by 3, so 2 times 3 to get 6. I don't multiply 6 by 3 to get 11, so it's not geometric. If I check for addition, I have a pattern of adding 4, adding 5, adding 6. This is not a constant rate of change, so this answer is neither. For our last example, from one number to the next, I am subtracting 5, subtracting 5, subtracting 5. Remember, that's the same as adding -5. So this is an arithmetic sequence. So we're going to extend this over to graphing and what it would look like. Remember, when we say position, that's like a batting order. So if I were to write this sequence out, how we're used to it from the prior example in a list, it would be 32, 16, 8, ... Okay, the batting order, that means what position in the lineup is that value. So my first position in the lineup is 32. That's why 32 has a 1. My second position is 16. Why it has a 2. The third position is 8. So how do I continue this pattern? So from 32 to 16 is multiplication of a half, multiplication of a half, or you can think of it as dividing by 2. So I want to continue. So I divide by 2 to get 4, divide by 4 to get 2, divide by 2 to get 1. We already know that this is a geometric sequence, and geometric sequences are related to exponential functions. So hopefully that's how my graph appears. So in position 1, I was at 32. Position 2, I was at 16. Position 3 was at 8. Position 4 was 4. Position 5 is 2, and position 6 is at 1. So as you can tell, it is not a straight line because we have different rates of change in between. This does create an exponential function. This is also exponential decay, which makes sense because our factor is a multiplier of a half. And any number between 0 and 1 causes a decay. Our second example looks like we have a pattern of adding 2. So when we add 2 to each value before, we end up with 3 and 5. A consistent pattern of adding 2 or subtracting is a arithmetic sequence, which will create a linear function. So I'm going to graph these coordinates, and we should find a line. So we have 1, -3, 2, -1, 3, 1, 4, 3, 5, 5, and indeed, we do create a linear function. The last thing we're going to do is we're going to write these as an equation. So if you recall back to linear functions, we would look for a constant rate of change. So it is an increase of 3, so that represents my slope. If we think of it like a batting order, this is the first batter, second, third, and fourth. Some of us, most of us, we went back and we said, well, we know the y-intercept has a x value of 0. So if I go backwards in my sequence, so if I go subtract 3, I'll end up with 10. So my y-intercept is 10, my slope is 3. So our final line, or our final arithmetic sequence, was y equals 3x plus 10. Where we can plug in any value into x to find any position. Like if I wanted to find the 10th term, instead of continuing, I can just plug 10 in for x. And the 10th term is 40. Arithmetic or geometric sequences are actually a little bit easier. Recall that A stands for the initial value and B stands for our factor, or what our multiplier is. So our initial value is -125. So I have y equals -125. Okay, I have to find out what the pattern is. So each value is being divided by 5. That is the same as multiplying by the reciprocal. So that's the same as multiplying each value by 1/5. So that is my factor, or that is my multiplier. So -125, we're going to multiply by 1/5. And it's always going to be raised to the x minus 1 power. So whatever term I want to find, like if I want to find the 10th term, all I'm going to do is plug that in for x.